Hello viewers, welcome back to the course on matrix computation and its application. So in the previous lecture we have started with that how we can check that the linear transformation is 1 onto or not. So for that one now we will continue with that concept with the lecture number 32. So in the previous lecture we have discussed that how we can check that the transformation from U to V, a vector space from U to vector space V, that T is 1 to 1 and or onto. So that we have seen. So for few examples we have discussed. So now I can discuss another example, very important example, like so previously we have discussed the linear operator D, that is a differential operator from the C1 space to see the set of all first derivative continuous function to the set of continuous function in the interval from A to B, and then we have discussed that D of f is basically f dash, or I can define that df by dx. So it is a derivative we have taken. Now I want to check whether D is 1 or onto. So this one I want to check. Now we know that, so let first we check about onto. So for onto we know that for any continuous function f belongs to the set of continuous functions C A B, we are able to take its antiderivative. So antiderivative we know that this is called the integral basically. So we know that every continuous function in the given interval a b we can take its integration. So from here I can, for any continuous function I can define its integral. So from here I can say that for, which implies that I can say that this transformation, linear transformation D is onto, because I am going from C any continuous function I can take the antiderivative, and if I take the antiderivative then this will reach to C1 AB, and this is the way we can show that if for any vector in the range space the CAB we can have a vector in the domain such that D of that function is equal to this. So by this way we can say that D is onto. So here D is onto means the range space of D is equal to the whole space CAB. So this is defined that D is onto. Now how to check 1. So it is clear from here that since we know that the set of all constant, if I take the set of all constant and I take the derivative d of dx, suppose some constant c, then I know this value is equal to 0. So from here I can say that the null space, that is NT, definitely will contain all the constant functions and some other functions that we do not know. It may happen that we will get some vectors whose derivative is going to 0 So, basically one thing is sure that all the constant functions that we are going to have, that is going to have the derivative equal to 0. So, in this case from here I can say that my null space is not equal to 0 space. So, this is not equal to 0 space. So, from here I can say that the operator D is, so the operator D, that the differential operator, I can say that this differential operator is not 1 to 1, because I have a constant functions which going to give you the derivative 0. So, in this case definitely it is not going to be 1 1. Similarly, now based on this one I just want to give some theorem. Let I take a linear transformation T from the vector space U to V. So, be a linear transformation, then so we know that the range space of T is a subspace of V. We also know that null space of T is a subspace of U. So, these are the few facts. Third one is that T is 1 1 if and only if the null space of T is the 0 space of U, 0 subspace of U, not the 0 space, I can say that 0 subspace of U. The fourth one is that if I have a set U1, U2 up to UN that spans U, then T of U1, T of U2, T of UN, that set spans range space of T. And the fifth one is that if U is finite dimensional, then dimension of RT is always less than the dimension of U, and the dimension of RT is also called the rank. So, you can write from here that the dimension of range space T is also called rank of T. So, these are the few results we want to prove. So, the first two results we have already proved when we have discussed about the matrices from AN to AM. So, these things you can check from the lecture based on that one, and it is very easy to show also. Now, I can write the first and second proof is have already been discussed. So, let us study about the third one. So, it says that my transformation is 1 1 if and only if the null space is a 0 subspace of U. So, let us prove this one. So, in this case what I do is that first I will check that let my T is 1 1. It means if the t is 1 1, then I can say that t, and also I know that t of 0 of u always map to 0 of v. So, this I can write then t is 1 1. Also this is true for all the linear transformation. So, if it is 1 1 and this is also true, so which implies that the null space of T will contain only 0 element of U, and from here this is we are able to show that NT is the only 0 subspace of U. Conversely, let NT contains only 0 element, that is a 0 subspace of U. Now, let T of U1 is equal to T of U2 for U1 and U2 belongs to U. I can write from here that T of U1 minus T of U2 is 0. So, 0 is in the V. Now, from here I can write like this one, the T of U1 minus U2 is equal to V, because this is the linear transformation. Now, from here, which implies that U1 minus U2 belongs to null space of T, because it is mapping to 0. So, it will belong to the null space of T, but null space of T is just containing the 0 element. So, which implies that U1 minus U2 is equal to 0, and that shows that U1 is equal to U2, and this is the way we can show, we can prove that, which implies that the T is 1 to 1. So, from here I can say that T is 1 to 1. So, if I need to check the linear transformation is 1 to 1 or not, we should concentrate about the null space. If we are able to find an element other than 0 element which is mapping to the 0 element under this transformation, then from there I can say that the given transformation is not 1 1. So, this is we are able to show. So, the next one is fourth one. Now, it is given that U1, U2, UN, the span is U. So, it is given to me. Now, from here we need to show that T of U1, T of U2, T of UN, if I take the span of this one, that is equal to RT. So, this we need to show. Now, from here what I need to do is that, so I will take the one way. So, let, so this is the, I am taking that let I take a element V belongs to, now I can one thing is true, that since T of U1, T of U2 and T of UN all belongs to the range space of T, and RT I know that is a subspace of the vector space V, then if this belongs to RT, their linear combination also belongs to RT, and from here I can say that the linear combination then I can write that linear combination of T u1 T u2 T un also belongs to R T, because I just take the linear combination, and by the property there is a linear transformation, this belongs to R T. So, from here I can say that their span T u1 T u2 T un also belongs to R T. So, from here I am able to show that, so belongs to R T. So, I can say that this is subset of R T, the span of this will be subset of R T. So, we are able to show one way. Now, so this is the one of the way I can say that, because to show that this is equal to this, we need to show that if I take the element from here, that should be also belongs to the right hand side, and if I take the element from the right hand side, it should belongs to the left hand side. So, we have shown that if I taken the element from the left hand side, then we are able to show that this belongs to the right hand side. Now, conversely, on the other hand, not conversely, I can write on the other hand, if, so what I do, on the other hand, let me take, let I take the element V belongs to the range space of T. Now, from here, if V belongs to R T, then I can say that there exists some U belongs to U such that T of U is equal to V, because it is a definition of the linear transformation, a transformation from U to V. Now, since U belongs to U, so I can write that U can be written as alpha 1 U1 plus alpha 2 U2 alpha n Un, because I have, it has been given that this U1 U2 Un they spans U. It means that any vector from U can be written as a linear combination of this one. Now, from here I can write, take the linear transformation Tu. So, I can write this as alpha 1 U1 alpha 2 U2 alpha n Un, because here I know that alpha 1 alpha 2 alpha n are scalars, that we already know, and this one I can write as alpha 1 T of U1 plus alpha T of U2 alpha n T of Un. It means that, and this is equal to my V. So, I can write that the V can be written as this one. So, I have started with the V from the R T, and I showed that V can be written as a linear combination of this one. So, which implies that V belongs to the span of T U1 T U2 T Un. So, this is the span. From here I am able to show that the R T is a subset of span of T U1 T U2 T Un. So, from here, from the equation 1 and equation 2, so from equation 1 and 2, we can write that the range space can be written as equal to the span U1 T U2 T Un. So, that is the way we can show. So, here you just check that we are, it has been given that the U1 U2 Un they are spanning the whole U. It is not given that they are linearly independent or not. So, if I take the set of vectors n vectors which is spans U, then I take the corresponding image of these vectors that will span the whole range space R T. So, this is the way we are able to show. Now, we have to show the next thing is that the dimension of R T is less than equal to dimension of U. The fifth one is we can check that the dimension of R T is less than equal to dimension of U. So, this is clear from here that now I can write from that from above result, that is the 4 one. If I say that if U1, U2, UN this set is Li, then we know that the given transformation is uniquely determined by the value of the transformation at its basis. So, it will be a basis of U, because they are spanning the whole U, they are linearly independent. So, it becomes the basis of U, and from here I know that the R T will also span by T of U1, T of UN. Now, it may happen that if T of U1, T of U2, T of UN, if this set is also Li, then dimension of R T is also equal to n, that is equal to the dimension of U, because it is a basis of U. And if the set TU1, TU2, T of UN is linearly dependent, then if it is linearly dependent, then I can remove those vectors which are the linear combination of the previous one. So, then I can say that the dimension of R T will be less than n. So, from here I can say that dimension or the rank of T is always less than equal to n, where n is the dimension of U, where n is equal to, I am taking dimension of U. Because why I am taking n? Because I have taken that this is a linearly independent set of vectors and n in number. So, I know that this is going to be, the dimension of U is going to be n. So, this way we are able to show this result. So, the next thing we are going to discuss is again about that. So, let us do that, how to find rank and nullity, how to find the rank and nullity of a linear transformation T. So, that we are going to discuss. Now, for example, I take the, suppose there is a transformation from V3 to V4. So, I just take one example. So, this is my linear transformation, be a linear transformation and define like x1, x2, x3, because it is coming from the V3 and its image becomes x1, x1 plus x2, x1 plus x2 plus x3 and x3. So, this is a linear transformation, it is given to us. Now, the question is find its rank and nullity. So, it is given to us that this is a linear transformation. Now, from here I want to check, find out the rank, means the dimension of its range space and the dimension of its null space. Now, let us discuss about the rank. Now, I know that this belongs to R T. So, R T is basically set of all the vector of this form x1, x1 plus x2, x1 plus x2 plus x3, x3. So, this is the set of R T, because it is belongs to. So, this R T I know that is a subspace of V4. Now, I can write this as x1 plus x2, x2 plus x3, x3. So, this one I can write in the form of, I can take x1 common. So, it will become 1 1 1 0 plus x2, it will be 0 1 1 0 plus x3, that is 0 0 1 1. So, I am able to find x1, x2, x3 from here. So, that is a way we can find. It means that this vector is a linear combination of these three vectors. So, I am able to get these three vectors. So, this is my first vector, second vector and the third vector. Now, from here I can say that my range space R T, from here I can say that it is R T is spanned by this vector. So, I can call it this one. Now, for the rank I need to check. So, we need to check about linearly independence or linearly dependence. So, these vectors are given to me. I can write this vector in the terms of a matrix as a column vector of a matrix. So, I can write here 1 1 1 0 0 1 1 0 0 1 1 0 and 0 0 1 1 1. So, this is my 4 cross 3 matrix. Now, I can convert this matrix into the row echelon form by, I can just make this element 0. So, I can write minus R1 plus R2 and minus R1 plus R3. So, this will be 1 1. So, it will be 0 here, 0 here and 0 here. So, that is 0 0. Now, I am taking minus 1 and 1 it becoming. So, it is 1 here and 0 here. Now, it is again it is 1 here, 0 1. So, I get this pivot element, this is another pivot. So, I will make this minus R2 plus R3. So, that will be 1 0 0 0 0 1. So, this will be 0 and this will be 0. So, I am taking here minus 1 adding to here. So, this 0 and this will be 1 1. So, I am able to get these vectors. So, these 3 vectors from here I can say. Now, based on this one I can say from here that rank of this matrix, rank is equal to 3, because all these 3 vectors are linearly independent, or the vectors are linearly independent. So, that things we have already discussed when we have discussed about the matrices. So, from here I can say that the dimension of R T is 3. Now, we have to discuss about the null space, about the nullity. Now, the set of N T is all the elements x1, x2, x3 belongs to V3 such that T of x1, x2, x3 is going to be 0. So, from here I will get that the set x1, x1 plus x2, x1 plus x2 plus x3, and this is x3, that is going to be equal to the 0 0 0, because this belongs to V4. So, and the V4, the 0 element of V4 containing the 4 elements, and from here I can say that equating the values. So, my x1, x2 is equal to x3, both all the 3's will coming 0. So, if all the 3 are coming 0, from here I can say that the null space of T will contain only 0 element of V3. So, from here I can say that nullity of T is 0. So, nullity is 0 and the rank is 3, and from here we can also observe that the rank plus nullity, that is here it is coming 3 plus 0, that is equal to 3, and that is equal to the dimension of the domain space V3. So, this way we are also able to show that rank plus nullity is equal to the dimension of V3. So, this is how we can find the rank and the nullity of the given linear transformation. So, we will stop here. So, in the today's lecture we have discussed some facts about the linear transformation, and then we have showed that from the given linear transformation how we can find its rank, that is the rank of the linear transformation, and nullity of the linear transformation. So, in the next lecture we will also continue with this one. So, thanks for watching, thanks very much.